Welcome to this explainer. Today, we're diving into thermodynamics, and honestly, this is the ultimate rulebook governing literally everything around us. At its core, it's really just the study of how energy moves, how it transforms, and how it drives the mechanics of the entire universe.
So, think about this for a second. What do a boiling pot of water, a rumbling car engine, and the expanding universe actually have in common? Well, the answer is pretty profound. They are all governed by the exact same set of invisible rules. That's right, the scientific laws dictating how you make your morning pasta, those are the exact same mechanics determining how galaxies evolve over billions of years. It's wild.
Here's our roadmap for today. We're going to break this massive topic into 6 easily digestible steps. We'll start with what is thermodynamics, look at classical versus statistical approaches, define our systems, dive into the laws of thermodynamics themselves, explore processes and cycles, and finally connect it all to everyday life. All right, let's jump right into section 1. What exactly is thermodynamics?
So, formally speaking, thermodynamics is defined as the study of the effects of work, heat, and energy on a system. Now, if we look back, this field actually kicked off in the 19th century. A French engineer named Sadi Carnot was just trying to figure out how to optimize early steam engines. He was looking for better mechanical efficiency, But from that super practical industrial optimization, an entire branch of physics was born, and it eventually redefined our understanding of reality itself.
The cool thing is, all of these complex interactions really just boil down to 4 main quantities: temperature, internal energy, entropy, and heat. If you can track these 4 parameters, you can map the energy state of absolutely anything. Temperature gives us our baseline thermal state. Internal energy, that represents the total macroscopic kinetic and potential energy. Heat tells us what's transferring across boundaries. And entropy, well, that gives us a measure of disorder. Put them all together and they create this sort of mathematical interlocking grid that maps energy flow perfectly.
Moving on to section 2, let's look at the classical versus statistical approaches.
When analyzing all these thermal properties, physicists basically use 2 different lenses. Classical thermodynamics looks at the big picture, the relationships between bulk properties of matter. So nothing is examined at the atomic or molecular level here. It treats matter as a continuous macroscopic medium. Statistical thermodynamics, on the other hand, wants to know why those bulk properties exist by examining the behavior of constituent atoms. Basically, you can either analyze the overarching system, or you can zoom all the way down to track the microscopic molecular kinetic energy. Now, for most practical engineering and macroscopic stuff, the classical approach is by far the most efficient framework. You can just directly measure things like pressure, volume, and temperature through everyday experiments. But the statistical approach, that's a bit heavier. It relies heavily on quantum mechanics and probability theory to track the average behavior of billions of colliding particles. It requires some incredibly complex math, but it gives us a much deeper fundamental understanding of why those macroscopic states even emerge in the first place.
Okay, section 3, defining systems. Let's set the playing field.
When we define a system in thermodynamics, we categorize it strictly by its boundaries. Take an open system, like a boiling pot of water without a lid. That exchanges both matter and energy with its surroundings, right? Steam escapes and heat radiates outward. Then you have a closed system, like a sealed pressure cooker. It contains its mass, so matter can't escape, but energy, in the form of heat, still crosses the boundary. And finally, an isolated system. This is the perfect theoretical vault where absolutely no matter and no energy can transfer in or out.
To measure these systems, we use what are called state functions. These are either intensive or extensive. Extensive properties, like volume or total mass, depend entirely on the size of the system. They scale linearly. But intensive properties, things like temperature or pressure, those are absolute. Think about it. The temperature is exactly the same whether you're measuring a tiny microscopic drop of water or a whole giant bucket of it. These properties define the intrinsic condition of the material, totally independent of how much of it you actually have.
Which brings us to section 4, the real meat of this explainer, the laws of thermodynamics.
We've got 3 primary universal laws that govern all energy flow and transformation. We call them the 0th law, the 1st law, and the 2nd law. So let's dive into their profound implications.
The 0th law is all about thermal equilibrium. It basically says that if 2 systems are separately in thermal equilibrium with a 3rd system, then they have to be in equilibrium with each other. It sounds super simple, but this is actually the foundational baseline for all empirical temperature measurement. It establishes the mathematical transitivity of heat transfer.
Without this law, the whole concept of a thermometer, or having a standardized scale of temperature at all, just wouldn't make any sense. It guarantees that heat stops flowing when interacting bodies reach identical energy states.
Next up is the first law, the conservation of energy. You've probably heard this one. Energy cannot be created or destroyed, only transformed. The governing equation here is delta U equals Q minus W. In plain English, the total change in a system's internal energy, that's the delta U, is precisely determined by the heat added to it, Q, minus the work done by the system on its surroundings, W. It's like the ultimate cosmic accounting book. If a compressed gas expands and pushes a piston, it's doing work, and that work has to strictly draw from the internal energy of the gas, or be offset by added heat. Every single joule is strictly accounted for. No free lunches here.
Then we have the second law, which introduces the famous concept of entropy. It states that in any isolated system, a measure of disorder called entropy always increases or at least remains constant over time. This is huge. This law actually establishes the absolute arrow of time and the spontaneity of our universe. It explains precisely why heat naturally flows from a hot cup of coffee into a cold room and literally never in reverse. It's why a dropped egg shatters into a mess on the floor, but those fragments never spontaneously reorganize back into a perfect shell. The universe inherently trends toward maximum disorder, meaning certain energetic conversions are fundamentally, permanently irreversible.
All right, Section 5, thermodynamic processes and cycles. How do we actually use this stuff?
Well, engineers design machines by mathematically constraining these different variables. It's like a cheat sheet for building engines. If a process is isothermal, the temperature is kept constant while heat exchanges freely. An adiabatic process perfectly insulates a system, so there's zero heat exchange, meaning any work done comes entirely from internal energy. Isochoric maintains a constant volume, so the system does zero physical expansion work. And isobaric keeps the pressure locked in place while the volume and temperature adjust dynamically. By sequencing these precise constraints, we can basically force nature to perform mechanical work for us.
And this precise manipulation of variables brings us to the Carnot cycle. Named after our guy Sadi Carnot from earlier, this describes the absolute theoretical, idealized limit for heat engine efficiency. The efficiency equals 1 minus the cold reservoir temperature divided by the hot reservoir temperature. It gives us an upper theoretical benchmark. But here's the catch. Real engines, whether we're talking about gas combustion engines or massive nuclear steam turbines, will inevitably always fall short of this idealized Carnot efficiency. Why? Because of thermodynamic realities like mechanical friction, chaotic airflow, and just unavoidable heat dissipation into the environment.
Now, conversely, we can actually use external energy to run this whole process in reverse. That forms the refrigeration cycle. Remember how the second law says heat naturally flows from hot to cold? Well, a refrigerator violently fights that natural flow. Through a continuous mechanical loop of evaporation, compression, condensation, and expansion, the system literally drags heat out from a cold interior and forces it into your warmer kitchen. But to reverse nature's inevitable flow like that, the compressor has to perform intense mechanical work, drawing continuously from your home's electrical grid.
And that brings us to Section 6, thermodynamics in everyday life.
These universe-governing equations are literally constantly at work right in our daily routines. Let's look back at our examples from the start of this explainer. Boiling water? That's a precise phase change driven by heat transfer, causing liquid molecules to break their bonds and vaporize. A refrigerator is a highly engineered loop of heat removal, fighting entropy every single second just to preserve your food. And a car engine demonstrates rapid energy conversion, detonating chemical fuel and transforming that thermal expansion into the mechanical work necessary to propel you down the highway.
So I want to leave you with this one mind-bending thought. If the second law dictates that in an isolated system, and remember, the universe itself is the ultimate isolated system, disorder and entropy are constantly, inevitably increasing, what does that mean for the ultimate fate of time and space? Thermodynamics implies that eventually, trillions of years from now, all energy will evenly disperse, heat will stop flowing entirely, and the universe will reach a final dark state of maximum entropy. It's a pretty heavy thought to end on, I know, but it really reveals the absolute, inescapable power of these universal rules.